Welcome back to the fourth video about the mighty Melexis MLX90363 Triaxis magnetometer. In the previous video, we implemented a total of 9 commands requesting magnetic field measurements from that chip. So we have 3 different kinds of magnetic measurements we can get back. First, just in 2 dimensions, a magnetic angle. Second, in 3 dimensions, the magnetic field direction. And third, the usual XYZ components of a magnetic field. Each of these 3 different magnetic measurements you can request in 3 different ways, called by Melexis trigger modes. And of course, we implemented the 3 different messages coming back from our chip to our master containing these 3 different kinds of data. Card here, link in the description. Now, in the previous video, we just used the trigger mode 1 and I gave you a short explanation about that trigger mode. But there are 2 more trigger modes and I want to cover those in today's video. And we might implement another MISO message in that context too. So, enjoy! Before we start, a short remark. It's meanwhile 33 degrees Celsius here and my studio lighting is still working, so that repair was successful. Card here, link in the description. However, I don't know if my brain will be able to operate correctly at those temperatures. We'll see. We already talked about trigger mode 1 in the previous video, so just a short recap here and one addendum. Basically, you start off with an SPI transaction sending a get1 command to the slave, which does the measurement stuff, and then in the next SPI transaction, you get the result of that measurement back. That's basically trigger mode 1, and it's called a trigger mode because that first SPI transaction with the command triggers the slave to start doing a measurement. And I moaned about that the minimum time between 2 of those SPI transactions is only referred here in the datasheet as T, SSREFE, and that this value is nowhere else mentioned in the datasheet. The reason being, it's probably a typo in the datasheet. Yeah. Datasheets can contain errors and typos, because when we advance 3 chapters here to 13.8 trigger mode's timing specification, we find the same timing information for the get1 commands or the get1 trigger mode, and here the minimum time between 2 SPI transactions is referred to as T REFE underscore mod 1, so mod for trigger mode 1. And that value is actually given in the chapter 13.8.1 if you run that thing on 5 volt, and in the chapter 13.8.2 if you run the chip at 3.3 volts. And it's in microseconds, not much, so all about 1 millisecond. And it's of course different for the 3 different kinds of data we can request. Just a short reminder, marker 0 means just the rotation of the field, marker 1 the 3D direction of the field, and marker 2 the XYZ components of the field. Let's skip over trigger mode 2 for now and continue with trigger mode 3. In trigger mode 3, you send obviously a get3 command to the slave and the slave does a measurement. However, the result of that measurement is not returned in the next SPI transaction, but in the SPI transaction after the next. So you have always an interleave of 1 additional SPI transaction until you get your measurement result you requested. Please note that unlike in trigger mode 1, where you have an SPI transaction and then the slave does the measurement and stuff, and then you have the next SPI transaction, in trigger mode 3 there is an overlap between the slave doing the measurement and the digital signal processing and the next SPI transaction. Also note that in this graphic the names of the timings here are also typos. The correct names are given again in chapter 13a Trigger Modes Timing Specification. And here we see that like Get1, where we have a TREFE underscore mod 1, we have here for trigger mode 3 a TREFE underscore mod 3, which is the minimum time between two Get3 SPI transactions. But in addition, we also have a TRERE underscore mod 3, which is basically the minimum period of Get3 transactions, or the inverse of it, the maximum frequency of Get3 transactions. Remember, the TREFE mod 1 in, for example, a 5-volt application and the marker 0, so just measuring a rotation of the magnetic field, was 920 microseconds. By the way, REFE stands for rising edge to falling edge on the slave select line. The TREFE mod 3 for the same scenario is only 90 microseconds. However, the TRERE mod 3, so rising edge to rising edge, that is the period or the inverse of the frequency of the SPI transactions, is for marker 0 at 5 volts 950 microseconds, so slightly longer. So what does that all mean? Let's assume we are requesting with Get1 an alpha angle measurement, so marker 0, and we have an SPI speed of 1 megahertz and we are operating our chip at 5 volts. Then our T rising edge, falling edge for trigger mode 1, so from here to here and here to here, is 920 microseconds. Our SPI transactions themselves, we're transferring here 8 bytes, so 64 bits plus a little overhead, about-ish 70 microseconds. Now we do the same with Get3 messages. So we have now to observe the T rising edge, so from one end to the transaction to the other end of the transaction for trigger mode 3 of a minimum of 950 microseconds. Our SPI transactions themselves are still, of course, 70 microseconds long. And you can already see that we are a wee bit faster in mode 3 in regards to how many SPI transactions we can send over the bus, also called the frame rate. But note, or better remember, I request a measurement here and I get the result of the measurement here. While in mode 3, I request a measurement here and I get the result of the measurement much later here. Now, what happens if we run our SPI bus at only 100 kilohertz with everything else being the same? It could be that you have very long SPI lines on your board or whatever, or you're using a cable for SPI and you cannot run it at 1 megahertz or 2 megahertz. Then our SPI transactions are 10 times longer because our SPI bus is 10 times slower. So we have here 700 microseconds. And for the Get1 commands, that means I have 700 microseconds. Then I wait again until the next Get1 command, 920 microseconds. And you can see things that is the frame rate compared to 1 megahertz, gets much slower. However, in trigger mode 3, the frame rate stays the same. I get exactly the same number of measurements per second from my chip with, the interleave, remember. The reason being, the time constraint here is from the rising edge of the previous transaction to the rising edge of the next transaction. So as our transactions have grown from 70 microseconds to 700 microseconds, they've just grown into that timing interval. Also remember, there is some parallel processing inside our little chip going on, so the measurement is done and processed while the SPI stuff is done in parallel. Of course, also in trigger mode 3, the frame rate will degrade as the SPI bus gets slower, because at some point our SPI transactions approach those 950 microseconds and stretch out everything. And we also have to observe the minimum of 90 microseconds between rising edge and falling edge of our SPI transactions. So in practice, with a very fast SPI bus, you would go usually for trigger mode 1, while when you have a very slow SPI bus, you would accept that interleave stuff and keep your frame rate up and go for trigger mode 3. That leaves us with one mystery. What does the chip deliver us here in the second Get3 message? Remember, we have no data here available yet. That's only in the third Get message of a sequence. So what is the chip delivering here? And the data sheet says in the second Get3 message, we get something back from our slave that's called Get3Ready. And that Get3Ready MISO message is empty. It has a marker of 11 for other message and carries the MISO opcode hexadecimal 2D. And of course, we find that message here also in the opcode table, and I just realized I made a mistake here because it has a marker 11 for other message. So it belongs to that block here, and this has to go. Sorry for that. To use trigger mode 3, we only have to make a few, that is 2 additions to our class. First, we have to add the Get3Ready member, hexadecimal 2D, to our enum class MISO opcode. And in the CPP file, we have to add that new member also to our MISO opcodes array in the valid marker opcode private function. In the sketch itself, I extended also the serial print MLX90363 last function here to print out Get3Ready if we get a MISO opcode Get3Ready within a other message. In the loop itself, I now print out what I'm exactly doing. The reason you will see later on. So first I do a send Get3 alpha, which I do here, and as usual I handle an error if one should occur, otherwise I print out the last received message. Then I have a delay in microseconds of only 900. Remember, the T rising edge for trigger mode 3 and alpha data is only 950 microseconds at 5 volts. But my code here uses some time to execute, and our SPI transaction itself should be about 35 microseconds. So this should be safe. Next, I do another send Get3 alpha. Again, handling errors, printing out the return from the client. Then I do another delay in microseconds of 900. And then I follow that up with a knob here. Again, handling error, printing out what the client sent back. And that should be here in the third statement. What we should get back here is actually the measurement we requested in the first send get3 alpha. And in the second send get3 alpha, we should get back that Get3Ready message. And the rest is the same. That is, I wait 500 milliseconds until I repeat the cycle. Let's see what our bad boy does with that code. Just plugging in here the USB, and opening the serial monitor. And stop auto scroll, and we're searching for a knob. That's the end of our cycle. So the start of our cycle is here. That's the first send get3 alpha, and that receives back from our slave a knob echo, because we ended the previous cycle, of course, with a knob. And then the next send get3 alpha gets back that new Get3Ready message. That's the Get3Ready message we created basically by sending the first Get3 alpha. And then we send at the end of our cycle in the loop a knob, and that finally gets an alpha message from not that get alpha, but the first get3 alpha. Let's scroll again and have a look. Diagnostic failed because I have the magnet here. Let's put that onto the chip. Okay, diagnostic passed, and we can see, our alpha is changing as I rotate the magnet. Wonderful. That leaves us with trigger mode 2. In trigger mode 2, you send a get2 command to the slave, and then the slave does nothing. It waits until it gets a sync pulse, and then it starts with the data acquisition and the digital signal processing and so on. And then with the next get2 command, you get the data you requested. And then the whole cycle repeats. You send another sync pulse, and then the data acquisition, etc. starts. And with the next get2 command, you get the data. Please note that the T rising edge sync and T sync falling edge names here for the timings are correct in that graphic, but they are drawn in the wrong way. We'll have a look at the timing diagram in a second. However, that sync pulse is nothing else than pulling low the slave select line for a defined duration. That's all. Why would you use trigger mode 2? Well, in case you have multiple slaves and you want to exactly sync up the measurements of each slave, then you can do that with trigger mode 2. I mean, you cannot send at the same time get2 commands to different slaves, so you do that in a staggered manner. But then pulling down the slave select line for all the slaves in a very narrow time frame, that's possible. And though you can synchronize the data acquisition and the signal processing and everything in several slaves. Anyway, here's the timing diagram for trigger mode 2, and you see, it's a T rising edge sync, but please note this is from the end of our get SPI transaction to the end of our sync pulse. And Yeah, in that graphic, it was from the end of our get2 transaction to the start of the sync pulse. I think this is the correct diagram because they were always correct and these were mostly wrong. Anyway, we also have here the T-sync falling edge, so from the end of the sync pulse to the start of the next get2 transaction. Here are the timings for trigger mode 2 for 5-volt applications. So the T-sync falling edge, for example for marker 0, is 874 microseconds, and that T rising edge sync is always 80 microseconds. Please note, if you add that up, you end up with 954 microseconds, and that's already more than the 920 microseconds you need to wait when you use trigger mode 1. Last but not least, the timings for that sync pulse. So depending on some internal setting, which we will talk about in a future video, the minimum length of that sync pulse on the slave select line is between 520 and 820 nanoseconds, and the maximum length is uniformly 10,000 nanoseconds, so 10 microseconds. In Arduino environment, I would say a sure bet is 1 microsecond. So, how do we implement that? I won't change anything to our class MLX90363 because I don't believe there's any use case where you would use that technique with a single slave. You will always use that with multiple slaves to sync them up, that is, to sync their measurements up. So instead, I created a new class, MLX90363 sync pulse. Standard constructor is not supported, but the constructor here has 2 parameters. First is an unsigned integer 8 array of, slave select pins, and then of course second parameter is the number of slave select pins in that array. And then we have a single public function send sync pulse, which returns nothing. It just sends that sync pulse on the slave select line. And as private variables, we have here the arguments to our constructor, the slave select pins array and the number of pins in that array. In the CPP file, we have that constructor, which does nothing else than initializing the private variables to the arguments we pass to the constructor. And then we have our public method send sync pulse. We have a local variable here, SPISS pin, which is used here in these loops, which just loop over all the elements in our array with the SS pins. And the first loop sets the SS pins to low, and the second loop sends the SS pins again to high. And in between we have a delay microseconds of 3 microseconds. I'll talk about that in a second. And those we create our sync pulse. That's it. I used 3 microseconds instead of 1 because the delay microseconds function in the Arduino environment has some oddities which we'll find further down under notes and warnings. And there it says this function works very accurately in the range 3 microseconds and up to 16,000 something microseconds. And we cannot assure that the delay microseconds will perform precisely for smaller delay times. So delaying 1 microsecond is really a little bit So instead I took 3. Please also note that you wouldn't use loops in a real-world application, okay? Because using these loops, you get, again, a little bit of delay between the measurements of your different clients. This is just for demonstration purposes. You would usually use port commands. So set port B, C, or D to a certain binary value to ensure that really all your slave select pins go low and then high again at exactly the same time. In the sketch, I create an additional byte array, MLX90363 slave select pins with, only one array member, that is our already existing slave select pin. And I also create an instance of that MLX90363 sync pulse object with, the slave select pin array and the size of the slave select pin array. In the loop, I do now first send get to alpha printout, because we do now send get to alpha. And the usual handle library errors and print everything nice what we receive on the 0 port. Then I do a delay of 80 microseconds. That was that T rising edge async mod 2 timing constraint. And then I call MLX90363 sync pulse, send sync pulse. And after that, I do another delay of 950 microseconds before I print that I do send a knob, and I send a knob, and error handling, print out on the 0 port, delay 500. So basically, that knob command here should give us our measurement data, hopefully. And that's what it looks like on the serial monitor. So where does our cycle start here? Let me stop the scrolling for a second. Set get to alpha replies knob echo, because the last command at the end of our loop is our knob. And then the send knob returns us a alpha data message. And of course the diagnostic fails, because as always I still hold the magnet here in my hand. So you know the game. I put the magnet here and we pass the diagnostic, and we are actually measuring the rotation angle of the magnet, as usual. That's it for today. A little bit shorter video this time. It's too hot. I mentioned that in the beginning. But important stuff here if you really want to use that little chip. So to summarize, usually you would just use trigger mode 1. Send an SPI transaction, get your result back in the next SPI transaction. If you are forced to use a very, very slow SPI bus, then you might switch to trigger mode 3. Keep the frame rate up at almost maximum, even with a 100 kilohertz SPI bus in our example. However, you pay for that with an additional interleave of 2 SPI transactions. So you request some data and you get the data back in the next after the last SPI transaction. And if you have several clients and you really need to take measurements with all the slaves at exactly the same time, you would go to trigger mode 2. That's it. Too hot. I don't know what we will do next time. Either we go into the configuration stuff or EEPROM writing would come first. I'll have to think about that. Anyway, till next time, Bye.